Let's do another example of combining thermochemical equations. You've got a couple of thermochemical equations for reactions where you know the delta H is, and you're trying to find the delta H for an unknown reaction. In this case, it's the formation of Fe2O3, which is rust. It is the form that iron is in a lot of iron ore. This first reaction is pretty important metallurgically because this is how people get iron out of iron ore. They use carbon monoxide to do that. They use it as a reducing agent. This is an oxidation-reduction reaction. And you might, for practice, find out what is the oxidizing agent and what is the reducing agent here, and how do the oxidation numbers change. Who knows? That could be a test question. All right, let's do this. In the last video, we looked at a step-by-step procedure for doing this type of problem, combining known thermochemical equations to get an unknown one. The very first step was write out the equation you want, the one that has the unknown delta H. We call that the target equation. This is the target. We're trying to find delta HF for this. But we have to write out the equation. Okay, now we know this is a formation equation because of the little f there. So that means when you write the equation down, when you see that little f, it means just write this as the one and only product. And it has a 1 in front of it. So that F tells you that's the product. Now what are the reactants? It's a formation equation. So you're going to write the two elements that you have here. And you're going to write them in their most stable forms. The most stable form of iron at room temperature and pressure is the solid. And the most stable form of oxygen is what? So now we've got to balance this. There's 2 irons in there, and there's 3 oxygens. Now I've got to keep a 1 in front of this, so I'm going to have to use fractions. To get 3 oxygens on this side, I'm going to have to put what here? Well, it's going to have to be something over a half. It'll be 3 halves. 3 halves times 2 will give me 3 oxygens there. So that's my target equation. That's the equation I want to end up with. Second thing, write out the steps. Okay, there's 2 of them up there, and they're already written out. These are the steps, so I'm not going to write them down again. I'm going to be lazy. I have them both up there, written out already. Third thing is, can you flip the steps to match the target? What I mean by that is, let's look at the target. It has iron solid on the left-hand side. Now if I look at this one, it's got iron solid on the right-hand side. So this is one that I want to flip. I want to flip it so that it is going to have the products as the reactants. And the reactants as the products. I'm just flipping it over. Now what's the delta H? What happens to the delta H when I flip it? If I flipped this, made this backwards, I have to make this backwards too. I have to flip the sign on it. Alright, so now that puts the iron on the correct side. I've got O2, I want on the left-hand side. Okay, this one has O2 on the left-hand side, so that's fine. I want to have Fe2O3 on the right-hand side. And this one has got Fe2O3 on the right-hand side. So I'm done with flipping the steps. 4. Scale the steps so anything not in the target will cancel. Okay. Let's see. What's not in the target that's in the steps? Here's my two steps at this time. This one and this one. Here's my target. Well, I don't see any CO2 in here, so the CO2's got to cancel. Now I've got 3 CO2s on the left of this one, but I've only got 1 CO2 on the right of this one. In order to make the CO2s cancel out, I'm going to have to multiply this equation by 3. So I'm going to cross this equation out, and I'm going to write it times 3. It goes to 3 CO2s. And then what's delta H for that? It's going to be 3 times minus 283.0 kilojoules. 3 times that, whatever that is. Alright, so now these are my 2 steps at this point. Now let's see what's canceled out. We've got the CO2 to cancel out. That's nice. What else needs to cancel out? There's no carbon monoxide in here. There's no CO, so that has to cancel out too. But look, there's 3 CO there and 3 CO there, so that works nice. Okay, so I've got it. I can go to the next step, add the steps. Alright, I'm going to write down everything that's on the left-hand side of the steps that didn't cancel. There's 2 FeS plus 3 halves O2. That's the left-hand side of the steps. Now the right-hand side, there's an Fe2O3 that didn't cancel. And that canceled and that canceled, so that's all I've got. That's an S there. Now what's delta H going to be? It's going to be plus 26.7 plus 3 times minus 283.0. Okay. So what does that come out to be? Something like, it's going to come out to be a big negative number. Something like minus 822.3 kilojoules. This is a very exothermic reaction. It's got a minus sign and it's got a big number here. So it releases quite a lot of heat. And in fact, iron burns fairly regularly, or fairly vigorously. If you've got a sparkler, that's the reaction that's occurring there. And it's producing quite a bit of energy in the form of heat and in the form of light. It can produce enough energy to actually melt this iron that is here too. Alright, so that's a more difficult one. You're in a position now to solve all of the problems that are in the worksheet. Now, I'm going to show you a shortcut. Suppose I had a problem that was like this. Find delta H for this reaction. Sodium bicarbonate is used to make washing soda, which is sodium carbonate. Let's put in the states. Solid, liquid, gas. Find delta H for that reaction. And there's a way to do it if you look up the delta H's. For the formation of everything that is in this equation. So if I find all the heats of formation, the enthalpies of formation, I can actually do this using this procedure. I'm going to need to look up a delta H of formation for each one of these things. Let me see. I've got a table over here on the side. I'm looking on it, and I can see minus 947.7 for sodium bicarbonate. This is all in kilojoules. And for sodium carbonate, what do I have? Minus 1131. For water, what do I have? Minus 285.9. And for carbon dioxide, I've got, what? Where is it? It's minus 393.5. Okay, so these are the enthalpies of formation for all of these. Now, the long way to do it would be my procedure here, and that will work. That always works. But when all of your steps are formations, like we've got here, all of the step information that we've got are formations. You can do a shortcut. Delta H for the reaction is going to be the sum of delta HFs for the products. Minus the sum of delta HFs for the reactants. Remember we said delta was final minus initial? That's the same thing that's going on here. So let's actually do the math here. What's the sum for the products? Well, let's see. If I add this to this to this, whoops, 1131 minus 285.9 minus 393. I'm just adding them up. Plus a minus is a minus, so I'm writing it a little bit more compactly. Minus, I'm going to put parentheses around this. The sum for the reactants. Here's the reactant. And there's two of these. So I have to say 2 times minus 947.7. All right? So if I pick up my calculator now and do this, I'm going to get something like plus 85 kilojoules. Now, that's a lot shorter than doing it my way up here, because I didn't have to write out all the steps. So I saved some time. I don't have to write out the steps, but I can only use this shortcut here when all the steps are formation. And not all the problems you've got in your worksheet are like this. Some of them have got formations for steps, but also combustions or other reactions. But if you look at the last couple problems on the worksheet, all of the steps that they're giving you are formations. So you can use this shortcut to do those kind of problems fairly quickly. All right, you ought to be in good shape to finish up the worksheet at this point. And this is our last video.